this is a quick summary of the contents of the next several videos. What we have is a steel ball and a grooved track, and the ball, if released here, rolls down the track. Now, I count 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, but much faster than that, and I do that kind of under my breath because if I say it loud enough that you can hear it. First place, I'm going to be blurring my syllables together. You're not going to be able to understand it, and I can count faster if I count a little bit under my breath, okay? So what I do is I count like, say 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, okay? And at the end of each count, well, I count the 8 count, and I see that the ball ends at one of these 3 positions. Now I release the ball, and I do this 3 times independently, and I try to spot where the ball is going to end. There's obviously some error in that. I don't eyeball it that well. I don't necessarily even have the best angle to eyeball it from. And are my counts consistent? Is my 8 count here at the same speed as my 16 count was when I did this, 2 8 counts, or when I did the 3 8 counts to get to 24. And then I do a 4 count to here, a 12 count, which would be an 8 count, and a 4 count to here, and so forth. Having gotten that data, there's a scale marked on the foam here. You can't see it. It's kind of out toward the edge. And the scale's marked in 10 centimeter increments. So when I measure the average position for each set of 3 increments, well, I mark what I believe to be, eyeballing again, an average position for each set of 3 measurements, and I measure the position of that set, estimating the number of centimeters. Remember, I have a 10 centimeter increment between markings on the styrofoam, and those markings aren't completely precise. So there are all kinds of possibilities for error in this system. In any case, when I do this, I mark I make a table, my counts, 1 up through 28. My positions, 29.5 centimeters here. That's just where the ball happened to be on that scale when I set up the ramp. And 82 centimeters here. Again, these are estimates. For each interval, the interval between 1 and 4, the interval between 4 and 8, the interval between 8 and 12 counts, I calculate the change in time, the change in the number of counts. From 1 count to 4 counts would be a change of 3. All the other changes are 4. And we start at 1, not at 0, because I started my count at 1. Okay, the positions are marked here, and the changes in position. I kind of put a delta Y here to indicate that these are the changes in position according to my observations and my measurements. Here I calculate the average rate of change of the position with respect to clock time. Now, I've written out that whole average rate of change of position with respect to clock time. I've abbreviated average rate of change. That's going to be delta Y over delta T, the change in Y divided by the change in T for each of these intervals, for the interval between every subsequent pair of observations. I also calculate the midpoint clock time. For example, the midpoint clock time between 24 and 28 would be 26, halfway between 24 and 28. Midpoint between 20 and 24 would be 22. And make the assumption that the average velocity, which is between the velocity at the beginning of the interval and the velocity at the end of an interval, occurred at the middle of the interval. So then I take the average rate of change and graph it versus the midpoint clock time, and I get a scatter graph consisting of these points. I manually fit a line, straight line, to these points, and I estimate my the coordinates of that line at 2 points, and I'll use those coordinates as a basis for obtaining the straight line, the equation of the straight line. Okay, you can see that I've estimated this point to be at 0.5, this one to be at 2.9, giving us a rise of 2.9 minus 5, minus 0.5, and 26 minus 0, for a slope of rise over run comes out to be 0.10. The equation of the line, therefore, if r stands for the y-coordinate in this case and t for the x-coordinate, it's y equals mx plus b. Slope times the x-coordinate plus b. Now the x-coordinate again is the time. The y-coordinate is the average rate of change of y with respect to t. I'm just using r to stand for that. And then I make the substitution. The average rate of change of position with respect to time is velocity. So I say the velocity is 0.10 t plus 0.5, and we have a formula for the velocity of this ball in terms of t as it travels down the ramp. So if t is 25, right at this point, I could put 25 in here, 0.10, that's going to give me 2.5 and 0.5. The speed should be about 3 centimeters per count at this point. Now again, it's important to understand that there are a number of big uncertainties in all of this. There's the uncertainty of where I positioned the line. Could I have come closer on the average to these data points had I positioned the line a little differently? How well did I do in locating these points and keeping my count consistent? There are clearly many factors that influence the accuracy of this model. Now, if I graph the data, I can see that a straight line isn't going to work. When I originally graphed it, we didn't have the curve imposed on it, but it's clear that a straight line graph is not going to be appropriate, so we ask, could this graph be quadratic? Now, what this graph is the position versus time. So we've just graphed the data from the original data that we measured. Okay, so we have position here, time, and counts here, and we have 28 is the maximum number of counts. We've just subdivided that into 7, 14, 21, etc. Position from 20 to 80 centimeters, and just lined off that graph, and here's a hand sketched graph. Okay, well, we ask, can we do a quadratic model? Okay, well, the quadratic model could be y equals at squared plus bt plus c. However, if we assume that the velocity is 0 when t equals 0, this tells us that the slope at t equals 0 would be 0, because the velocity is the rate of change of this position with respect to time, and if the velocity is 0, that rate is 0. That's going to give us a flat graph. So we assume that the vertex occurs here, because that's where I released the ball. So assuming the vertex is at 0.28, we could put the equation into this form. We don't know what the values of a, b, and c are. So instead of using this standard form of the quadratic, we use this form, the form that we would use to graph the function by transformations. You can see that this is this function, the graph of this function would be obtained from the graph of y equals t squared by doing a vertical stretch by factor a, shifting the graph h units to the right and k units up. Now, if that's the equation, handling this board, I apparently brushed against it. This equation, with this assumption that the vertex lies here, tells us that the horizontal shift is 0, because the vertex lies on the y-axis or the vertical axis, and that there's a vertical shift Now, I'm not sure I said that right. There's a horizontal shift of 0. H is 0. This graph of y equals t squared would not be shifted to the right or left because the vertex remains on the vertical axis. We shift 28 units up to get to this point. So the vertex is at 0, 28, and that means that h is 0 and k is 28, so that the function is just y equals at squared plus 28. And that's just what we get if we put 0 in for h and 28 for k, and all we have left is to find a. To find a, what do? Well, I look at the graph and I assume that the point 2884 lies on the graph. I'll emphasize that 2884 assumes that the graph is a little higher than the one I drew here that went right through this point. Okay, we never assume a data point. So I'm assuming that I should have made the graph just a little steeper here instead of going through 2882, which would correspond to the data point. We go through 2884. So we assume this point is on the graph of the best fit curve. Okay? Y equals 84 then when t equals 28. So substituting that information into the equation, y equals at squared plus 28, we get 84 equals a times 28 squared plus 28. Now, I'll emphasize that the 28s here are not the same. Okay, the number's the same, but they have different meanings, and this is just an unlikely coincidence, and there are all kinds of unlikely coincidences that have occurred in this whole analysis and the data. This 28 is 28 seconds, this 28 is 28 centimeters, so really what this means is A is 28 seconds squared plus 28 centimeters. The two 28s measure completely different things. They just happen to come out with the same number. We easily solve this for A. We get A is 84 minus 28 over 28 squared, which is, okay, 84 minus 28, another coincidence, is 56, which is exactly double 28. So I divided one of these 28s in the denominator into the 56 we get here. I get 2, leaving the other 28 in the denominator, and you don't need to understand that. I said it pretty fast. Just an intermediate step in a calculation. That comes out about 1/14, which is very close to 0.07. So we finally obtain our model that I've circled in the middle of the board here. Our model is 0.07 t squared plus 28. And that's a model of our position versus time function. Do remember here that I'm compressing a longer discussion. There are a lot more details in the full discussion in the videos that follow this one.